Hey, everybody. All right, so here's another example of a hypothesis test with uh, two samples. In this case, we're going to look where we're still comparing means. We still have independent samples, so they're both going to be simple random samples, and there's no connection between them. And our standard deviation of the underlying populations for both samples is unknown. So the way this setup works is, um, first there are let's say some distributions for some characteristic for some populations, and we are each of these will have a mean, right? That I'll call mu1 and mu2, and we want to compare these means, right? There'll be something that we think is true about these means. One of them is greater than the other. Typically, our null hypothesis will be that these two means are equal. That doesn't always have to be true. I'll do an example later of a different type where that's not the case, but often the null hypothesis is that they're equal, and our alternative hypothesis is that one of them is larger or smaller than the other one. To test that, we will gather samples. Let's say x bar 1 and x bar 2, each coming from these respective populations. These come from sample mean distributions, right? And these are the sample mean distributions that we talk about when we talk about our central limit theorem, okay? And so that's kind of the setup that's in the background. And so once but because we don't know the standard deviations of the underlying populations, in this case, we're going to be using a t-test. So our test statistic, and I should put in parentheses here, I'll just put it down below. Because we're gathering samples and getting these sample means, we can also get sample standard deviations for each of these, right? So we will have that information, okay? And so when we conduct a test in this way, we compute a test statistic that's going to be a t-score that has the following formula to compute: x bar 1 minus x bar 2, right? Our comparison of our sample means, minus mu1 minus mu2. Remember, our null hypothesis is often going to be that these two are equal. So this term is often 0. And maybe I'll mention over here, right? We are also, by doing this comparison, we're creating another distribution, the sampling difference distribution, that under the null hypothesis would have a mean of 0 if these two things are equal. So this is really just the same comparison, or the same computation of the t-score when we were doing single means, except now our sample mean is a sample mean difference, and our mean is a difference of means, but it's the same idea. And down below, we're going to have our standard deviation, but the way we compute the standard deviation for this new distribution where we're comparing a difference of means, we take the standard deviation of the first sample and square it and divide it by n1, that's the sample size. And then we'll do the same thing to the standard deviation of the second sample, okay? So everything here would be given in the context of the problem, or if you're a researcher, this is all information you go out and gather. And then this is the computation for the t-score. When we have a student's t-distribution, we also need degrees of freedom. And so this is a relatively complicated formula that I'll just write out. We have something similar to what we saw in the denominator over there. We're taking these standard deviations squared, dividing them by their sample sizes and adding them together. But here we're squaring it, and then we're dividing by 1 over the sample size of the first sample minus 1 times its standard deviation squared over the sample size, that whole thing squared, and then the same thing for the other sample. S2 squared over N2, and that whole thing squared. Okay. So that's an ugly formula, but again, this is something you can do with a calculator. There are online calculators that all you need to do is put in the relevant values and it'll do it for you. Or when I was doing some practice problems, checking some of the homework problems and such, I just built a little spreadsheet where I could just enter in these things, S1, S2, N1, N2, X bar 1, X bar 2, all that kind of stuff. And then had the computation pre-programmed. So it would just spit this out so I didn't have to type it all together each time. There is also often people will use a slightly different version, a much easier thing to compute, but it also makes it harder. Sometimes people call it the conservative estimation of the degrees of freedom or something like that. It's going to be a smaller degrees of freedom, and if you recall, the greater the degrees of freedom, the more normal our distribution looks and pulls more information towards the center. Having a higher degree of freedom makes it easier to reject the null hypothesis. So sometimes, to be conservative, people will choose this version for the degrees of freedom. It's much, much easier. You just take the sample size of the first sample and subtract 1 from it. You do the same thing to the second sample size. You compare these and take the smaller one. So the minimum of 1 less than the 2 sample sizes, right? So obviously you can compute that in your head. It like I said, makes it harder to reject the null hypothesis. So depending on what people are doing, one or the other is used. So we will consider the top one the formula we're using, though there will be problems where I'll suggest using the other one, or homework problems that have that instruction to use the alternate conservative method. All right, let's do a problem so you can see how it actually works. So here's my sample problem. Good Grocer, grocery store, claims they have a faster checkout time. We're measuring this in seconds per item than their competitor, A Plus Grocery. Good Grocer conducts a study to back up this claim. They sample 13 people at their store. They find a mean of 12 seconds per item and a standard deviation of 2.3 seconds per item. 17 people are sampled at the other grocery store with the mean time is 14 seconds per item and a standard deviation of 1.9 seconds per item. We're going to conduct a test with 0.05 level of significance for the claim that Good Grocer has faster checkout speeds, right? So I'm gonna write this out in some detail. You don't always have to do this, but just to sort of see the structure that lives underneath. There's a distribution of let's call it checkout speeds in items per second or seconds per item, checkout speeds for Good Grocer. And there's a similar distribution of checkout speeds at A Plus Grocer, right? And what we're doing is taking a sample from each of these, and when we take the sample, we're then considering these sample mean checkout speeds. Sample mean checkout. Let's make this simple. I'm just going to call it sample mean speed for Good Grocer. And in the case of Good Grocer, our sample size is 13. Let's call this N1. And then there's this sample mean speed for A plus with a sample size of 17. That's our N2. Okay, so that, again, you don't have to write all this out, but it's probably a good idea to at least attempt to understand this. That's behind the scenes what's happening. And so with that in mind, the data that we have for Good Grocer, we have a sample mean of 12 seconds per item. So I suppose this time must include like bagging and all that stuff. It shouldn't take 12 seconds to check out one item, but it's probably taking an average over your entire trip through the line, I guess. But anyways, we get our sample mean of 12. We already said we have a sample size of 13, and then a standard deviation is given of 2.3 seconds per item. I'm leaving the units off just to make it simpler down here. All right, same thing for our A plus grocer. The sample mean time is 14 seconds. The sample size is 17, and the standard deviation is 1.9. So remember, this is standard deviation for the sample, not the population, which is why we have to use t-score. So there's all our information summarized. Let's write our null hypothesis. Our null hypothesis is that mu1, right, that's going to be the mean of the first distribution. Mu1 is less than, the null hypothesis is that the checkout times are equal. Let's put, yeah, we can just put equal, it doesn't matter, equal to 0. The alternative hypothesis, the thing that we're testing, the claim that we're making, is that mu1 is less than mu2, faster speeds, right? Fewer seconds per item, which would mean when we subtract them this way, because we're suggesting that mu1 is smaller than mu2, mu1 minus mu2 would be less than 0. So that's our alternative hypothesis. This also means we're doing a left-tailed test, right? We're looking below because we're looking at below 0. Okay, so there's our setup. Now we want to compute, yeah, let's do down here. I want to compute my t-score, right? So I'm not going to go through the whole computation. This is something that just happens in a calculator, but I'm just using this formula, right, that I wrote here. Actually, maybe I can grab that. Let's see if I can remember the controls for this. There we go. There's copy. And come down here. And all right, there's our formula. So I'm just plugging the values into this equation. All right, so just copying the values from above into this equation. So using, there they are all listed right there. So we would have 12 is my x1, minus 14 is my x2. We're under the assumption, just like all our hypothesis tests, that the null hypothesis is true, which means that the difference between these two is 0. So that term becomes 0. Then we have the square root of s1 squared, so 2.3 squared divided by n1 was 13, plus s2 squared, 1.9 squared divided by 17. And when I computed this, I got negative 2.541. I used this complicated degrees of freedom equation that's up here, just plugging everything in, and I got degrees of freedom, it's 23. Note, when you plug everything into that complicated formula, you're going to get something with a decimal. I always just round it down, right? That's the conservative thing to do. That you're by rounding up, you're sort of implying that you have better accuracy than you actually have, better data than you have. Okay, so our degrees of freedom is 23, and now it's just like testing with any hypothesis test, whether we're doing one mean or two mean. I can compute this using a student's t-distribution calculator. What's the probability of getting a t-score less than or equal to negative 2.541? And what calculator, I used a calculator and got 0.009. Note that this is less than 0.05, which was our level of significance. Okay. Alternatively, you can look at the critical value, right? Remember what the critical value is. Since we had a 0.05 level of significance, I'm looking for the t-score on a student's t-distribution with 23 degrees of freedom that has 0.05 area below it. The t-score I found using an inverse student's t-distribution calculator was this. And we see that our t-score negative 2.541 is below that. So we could also note, it's another way to complete this test, say that our t-score, our test statistic is less than our critical number, and we're on a left, our critical value, and we're on a left-tailed test. Both of these results tell us the same thing, which is we have evidence to reject the null hypothesis. And we believe that good grocer, remember which is which, good grocer has faster checkout times than A plus grocer. Okay. All right. So that's a pretty typical kind of test. This is much more common than the example we gave where you somehow know the standard deviations for the population. And so this is, but it's, very simple or computation. Obviously, when we're doing more than one sample, the formulas get a bit more complicated, but it's really not that tricky. You have to classify what case we're in, right? Let's look at our classification that we have two means that we're testing. We're comparing two means. Independent samples, meaning there's no connection between the samples. We'll be doing examples later where, right, maybe we test something about a group of people, give them some kind of treatment, and then test them again. So the samples are actually the same. That's going to be a different kind of test. But here we're just taking two random samples. So we have these two stores. We have simple random samples of customers at each store. And then, of course, in this case, the standard deviation of the populations are unknown. When that's the case, you just have to pull the information out of the problem and plug it into these two formulas, as I did here, and then compute the test. Once you've got your test statistic, it's really just like computing any of the hypothesis tests we did before. It doesn't matter that it came from two means. The analysis at the end is the same. Okay, that's it. I'll be doing a couple more examples in the following videos.